Recording now.
Right. So welcome to our Data Science Club seminar series. Today we have Oliver giving us a really interesting talk on identifying bias in machine learning using examples from facial recognition. And thank you, Oliver, for presenting to us again. And we're really looking forward to your talk. Take it away.
Yeah, absolutely. Thanks for having me here. Let me go ahead and share my screen. Oh, I think I'll need
Oh yeah, sorry.
no worries.
Share. Okay, now you should be able to.
Great,
Francisco.
Yeah.
All right, everyone should be able to see my presentation now, yeah?
Yeah.
Yeah.
Cool. Let me go ahead and do this. Move my notes down here. Okay. Yeah, thanks everyone for stopping by. We're going to be talking about fairness and bias in machine learning with examples in computer vision and facial recognition. So, first I'm going to use fairness and bias kind of interchangeably in this talk. I'll give a quick definition of both here. Overall bias is a pretty overloaded term, like we use it in a lot of different situations. Here when I talk about it, I mean the presence of different model outcomes for groups of individuals, or for groups or individuals who should not have different outcomes, where groups are defined using variables like race, ethnicity, gender, age. And then fairness, which is a term that's used a lot more in the general computer science literature. When I use it here, I mean the absence of bias, and it presents measures of fairness that can indicate whether a model is fair or not. So why are fair models important? Well, I mean, machine learning makes up a lot of the infrastructure we see around us, even some of the infrastructure we don't see around us. And it helps to automate decisions, to make them faster, and to do it at scale. And so this can be done in a fully automated way, much like searching on Google, or maybe in a kind of way where healthcare professionals lean on computer decision support as another input to their decision-making process. So some examples of machine learning include recidivism. So that is predicting who's likely to reoffend again in the criminal justice system, or identifying criminals. And the reason I put criminals here in quotation marks is because this is also kind of a little overloaded. You have machine learning being used to compare an image of a suspect against a database to try and find out, who this person could be. Or there's a paper that came out, I want to say a couple years ago, on automated inference and criminality using face images, which dealt with looking at someone's face and trying to identify, is this person a criminal or not? And then the authors went a step further and tried to identify what are criminal features in a person's face. And if that made like anyone's skin raise a little bit, or like hairs raise a little bit, the reason is because like that is a throwback to something called physiognomy, which is using someone's facial features to determine their characteristics. I think a lot of people had just kind of agreed that that's like just not a good thing to do, but it's starting to pop back up again in computer vision specifically. And then there's also healthcare resource allocation using machine learning. And this is one I want to jump into a little bit, this dissecting racial bias in an algorithm used to manage the health of populations. What the authors tried to do here was to identify patients who would be high resource, or who would use a lot of resources in the clinical setting, so that they could intervene earlier and identify these patients and get them help earlier. The way they decided to do this was to use a proxy of healthcare costs, with the idea that if you are sicker, if you're going to need more resources, you're going to cost more within the healthcare system, which seemed to make sense at the time. They created a model to do this. It was actually very accurate. It performed very well for both Black and white patients in predicting healthcare costs. But when they took it a step further to try and look at, a different measure of sickness, and the number of ICD codes that this patient comes out of the hospital with, they found that Black patients were significantly more sick than their counterpart white patients, even at the same risk score of this algorithm. And so the way they fixed this was actually not changing the data or changing the algorithm, but was changing the proxy that they were trying to optimize for. So they didn't use healthcare costs anymore. They used a different one that took into account disease codes. And so these are some pretty good examples of, even when you have good intentions of using machine learning to help with healthcare resource allocation, you can have issues with that, especially because in this situation, you're essentially trying to allocate scarce resources. And then you also see examples of, identifying criminals and recidivism, where maybe this shouldn't be a process that totally is up to computer systems, because then the question comes up, who gets to opt out of these automated decision-making processes. So in this paper, the perpetual lineup, it was found that Black people are much more likely to be subjugated to automatic facial recognition than white people. And that's no accident. That's exactly how the system was designed. Even if the model itself wasn't designed to be used that way, that's how it ended up being used. So that's why it's really important to make sure that the models we're using are fair and treat different groups as equally as possible. So how do you define bias or fairness in this sense? There are lots of different definitions that exist. In U.S. law, there's something known as disparate impact, which deals with labor laws and housing, and it's basically saying that if a minority group, I think, has an adverse treatment compared to the majority group 80% of the time, then that policy that's in place is said to be discriminatory. And now, some people have tried to apply that straight to machine learning, but a lot of other different ways of measuring fairness and bias in machine learning have popped up anyway. There are a couple resources here which are really great if you want to read up on different ways to measure fairness, but some of the main ones that come up a lot is fairness through unawareness, which is the idea, can a model be biased if it doesn't see color? Really quick hint, it can totally be biased anyway. Then there's something known as group fairness, which is the idea that similar outcome probabilities between groups, and then individual fairness. So if two individuals are similar, given some kind of distance metric, then their outcomes should be similar as well. So a lot of questions that come up, once we're able to measure bias and fairness is, where does this bias come from so that we might be able to address it? One of the main ones that people will talk about is from the data. So it's kind of the garbage in, garbage out idea, but it's bias in, bias out. And because these models are learning from historical data, they will go through and basically perpetuate any biases that you have in that data. And it can also come through feature engineering. So how well is reality represented? What kind of categories are you using to represent people? Are those accurate with how they want to be perceived, how they are perceived? Context is very important in that setting. Model design and evaluation. So as I mentioned in the healthcare paper, they use a proxy of healthcare costs, which actually turned out to not be a very good proxy to be using. And so the way you design your model and how you evaluate it can have a big impact on what kind of bias you're going to be seeing. And I really want to note here privilege hazard, which is, the people usually designing these models are not the people who they're going to be applied to. And they may not even be the same group. They may not have a lot of interaction with the group that these models will be applied to. And so there's some kind of spots they may not know about when designing these models. And then kind of the more meta idea, which is experimental design. So what is being modeled and what kind of questions are being asked just in general. So I've included here some questions to ask yourself when designing machine learning systems. These are kind of like suss out your own biases that may be incorporated into the machine learning pipeline. And finally, it's important to note that there are lots of societal implications for automated decision-making and assistance. It doesn't just have to be something like recidivism, which I think is pretty obvious that there's going to be societal implications, but even something as simple as identifying someone's, I should say simple within quotation marks, as simple as identifying someone's gender within a picture for Facebook, for example. So today in this work, we're going to be in this tutorial, we're going to be really focusing on how to accurately represent people and how will this model be used once it's out of your hands, as well as featuring bias. So we'll be going over just one example of how to measure fairness in a model, and then kind of asking questions of, since we're going to be dealing with gender and also race and ethnicity, asking the question, do the categories that we're using actually even make sense? And so, hold on a sec, sorry. Right, this first paper here really talked about how when computer scientists are defining these models to identify someone's gender from a picture, they often don't really explicitly define what is their concept of gender that they're using for this model. And more often than not, it comes down to a very simple binary, male or female, and that completely leaves out people who are non-binary. And they also found that these models did very poorly on transgender people as well. And the fact that these models simply cannot take into account self-identity because that's not something that you can necessarily see. And then when we're talking about categories for race and ethnicity, there's been a lot of questions on how should we even use race and ethnicity in biomedical publications, especially when this can be almost implicit in some of the tools that we use. And some of the issues that were raised in the use of race and ethnicity in biomedical publications paper is that these race and ethnicity categories are pretty limited, and they don't account for the fact that these identities can change. They don't really lend themselves well to being put in one box or even two boxes. And a good example of this is the idea of blood quantum. So what blood quantum is a lot of Native Americans will carry around a card that tells you exactly how much Indian blood we have. And this isn't something that we've put on ourselves, but more that the US has put on us. And it's a way to measure exactly how many Native Americans there are in the US. And there's a lot of reasons for why this measure was being used or and is still used, but it has nothing to do with how we would define being a Native American. And so I think with that, I kind of want to bring to the forefront that these categories that we're using to define gender, to define race or ethnicity, really are, well, a lot of the times they can just be arbitrary, or they can come from political or cultural reasons. And they also do exert power over certain people too, which is why I think it's important to examine not only the fairness of a machine learning model, but also the biases that we incorporate into these models. So with that, I can move on to the coding section, unless anyone has any questions they want to ask. Cool beans. So I think everyone should have access to this. Let's see. Yeah, this Jupyter notebook. There'll be a GitHub link that people can follow afterwards as well. But what we're going to do in this is kind of go over this gender shades, intersectional accuracy disparities in commercial gender classification paper. We're going to try and repeat this experiment, but with a little bit lower quality because I don't have access to all the data that they used or the models. But I definitely suggest people reading this paper because it's really great. So we're going to go ahead and load the libraries that we need. And I'm glad that worked because I had a feeling it wasn't going to work for a second there. But so I have an image here called deadpool.jpg or JPEG. And we're going to load that in with the image library that I have here, which is from PIL.
Oh, actually, sorry. Could you paste this link into the chat? I was not able to find it. I don't know. Yeah.
Let me go and find that GitHub really quick for y'all then. Let's see. Okay, and then find, I think I've stopped sharing for a bit to find the chat. Hold on a sec. Cool. All right, that should be in the chat now.
Thank you.
Cool. So let's see, we're gonna go ahead and load in this image. Let's call it Deadpool. We use the image library, and they have a really great, just super simple open function. We pass it in the path of where that image is. And then one thing that you can do is once this image is loaded, I think you can just call, let me try and do that really quick. It loads up like that. And so what this is right now is a, it's a pillow or pill specific object. What we can do is we can turn that into something that a lot of us are probably much more familiar with, which is a matrix from Numpy. Let's go ahead, and the really cool thing is you can just pass it in the actual image object, and then you can use matplotlib to show that image. Oh yeah, I misspelled that. So it's pretty simple, and then this way we can actually work with this in a lot of things. Oh, sorry, does anyone have a question?
No, I just said wow.
Okay, cool. So now it's a matrix, and it's much more easy to work with. We can see that it's a 1100 by 2000 by 3, and so this is, I think, the height and width, and then this is the channels. So I think that's red, green, and blue. And if you're working with a grayscale image, I think that'll just be 1 right there. So we can also take, yeah, we can actually work with those channels too if we wanted to, using the image library. So we take our Deadpool object. So this is not the matrix one. This is the actual one read in from the image library. We call split, and that's what that's going to do is it's going to split the Deadpool image into its 3 channels, and then we can show it. We're going to convert that into an array right here. Let's just take the red channel and then call cmap equals gray. So that now we have the gray, or only the red channel for this one. We can try the green one too. Cool. Okay, so this is some code that I snagged from this GitHub right here. And all it does is it takes an image and then resizes it to a 200 by 200 pixel image essentially, and does some padding where if it's too tall or too wide, it'll just pad that with black. So the reason we're doing this is because I'm working on a little dinky CPU and can't actually handle all the images that we're going to be loading in, so we just need to make them a little bit smaller. But the first thing we're going to do is we're going to run through and start loading in images with this function, which isn't quite done yet. And this is where some pathing information is going to come into play. So I have this folder called data right here, and in it is 3 test, train, and valid. And so if you go into test, it already splits it up into men and women, and then we can look at the images here. So these are all different images that we can load in. They're already split into men and women using a very simple binary. And we have the test and train and valid files too. So what we're going to pass in is just these, a list of paths that we're going to be drawing data from. So data/train, data/valid, data/test. And then within each of those inner folders is going to be a man and woman folder. So we're going to code up how to exactly work with some of this, to work with these images, load them into NumPy arrays so that they can then be fed into a machine learning pipeline. Because a machine learning pipeline and sklearn can't work directly with images. They need to be put into the format of matrices first. So I'm going to go for IDX and folder, inner folder in enumerate, inner folder list. So this is just going to go through these inner folders here. And then we're going to do another loop that's going to iterate through these. So all image has equals, if anyone hasn't used glob.glob before, it's a really great library that allows you to find basically all the files that have a certain extension or certain path kind of name that you can use some regular expressions to define. And so I'll show that really quickly right here. I'm going to call os.path.join, which is just going to basically concatenate a couple strings for us. So path to data, which is this one, and we're hold on a sec. Yeah, and then we're going to put in the inner folder, and then what we're going to do is we're going to add in the star.jpg. Let's see, I think I messed up on one thing. Yep, an extra one there. Yeah, okay, but let's really quickly, I think that was probably a lot, so let me show you what that does really quick. So then let's take this one, and the inner folder, / oh, not there. Data / train, and then we're here. I think that one is / oh yeah, so I got that wrong because I was using that in a for loop before. So basically what it did is it took these data / train, concatenated that with this string here, woman, and then it found everything that has star, just as a wildcard, so anything, and then .jpg. So we're going to do that, and then we're going to iterate through that list of all images, which is going to be something like this. For image path in, so I know I'm using a lot of new libraries here, but TQDM, something you can wrap your for loops in, and it just gives you a progress bar of how it's going when it's looping over things. Image paths, right? Yeah. Okay, so let's do a quick sanity check and then just print image path really quick. Let's get rid of this one, and then see what that looks like. Actually, no, we should probably continue the rest of this function. Yeah, okay. And then we're going to call image equals image dot open like we did before, but now we're going to pass in the image path. And then we want to use this resize function right here. And I'll show you a little bit about what that does with this example. So we're going to give it our original Deadpool image, and then we're going to create something called small pool, and then turn that into a matrix and show what that looks like using the plot function. So what you can see here is that now it's 200 by 200, whereas before it was much larger. And since it was wider than it was tall, it had to introduce some padding to be able to resize it properly. So we're just going to try and do that same thing here. We're going to go image equals resize image, and then param equals image. Because all this takes in is an image, and then all it puts out is a new image of the same type. And then what we can do is we can turn that new resized image into a array. So call numpy.as array image. And then what we're going to do here is we're going to take this, we want to keep track of all our NumPy arrays in here. So we're going to append that to that list. And because we're doing some machine learning on a binary classification, we also need to know if we're looking at women or men in this one. And the way we're going to do that is kind of a little cheeky way of saying, So we're iterating through this. This enumerate, what it does is it's going to spit out, each folder within here. So one and then man. It's also going to spit out an index. And so it's going to be 0, 1, and that would keep going on for however many you have in that list. But we can just use that as an indicator for what class we're dealing with. So we just append IDX. And let's hope that works, because I should have introduced more debugging there, but I think that'll be okay for now. So let's go ahead and call that function equals, I'm going to load the image. Let's see. We have load image data, and then what we're doing here is we're iterating through the train data, the valid data, and the test data. So we're going to pass it in path to data because that's the only argument it takes. And what we're going to return is a matrix, a 4-dimensional matrix, and we can look at that in a sec after it's done. We're going to store these into this data dictionary. So what's going to have is train, valid, and test, and that's going to be the keys, and then the value is going to be a list of the X data and then the Y data. So data name is going to be, we're going to do some splitting really quickly, some string splitting. So to data.split, and then we're going to split on the slash, and then we're going to take the second to last one, and that may seem like a little weird, but you'll see why in a second. It's going to catch, actually it's going to catch this if we split like that. And then we can go ahead and say data dict at data name is going to be equal to a list of X and then Y. And let's go ahead and make sure that's in the library.
Wait, why are you doing this?
Mm-hmm.
Why are you doing the split? Why don't you just like call the second to last element?
Yeah, so like let's take a look at this one really quickly. By the way, these progress bars, that was TQDM doing that. You don't necessarily need that, but it's just nice to have. So you were asking why we're doing this split. So what we want is we want this one. And so if we call dot split on, I think this slash, what that returns is a list. And because it's ending with a split at the, or a slash at the very end, we need to call the second to last element in there. And that gives us test. Is that what you were asking?
Oh, it's ignoring the data slash part. Okay.
Yeah. So split's pretty nice for doing that with working with paths if you want to get a certain part in there too. So that was a lot. So let's take a moment to look at our X and Y data really quick. So we see that this is 340 by 200 by 200 by 3. This should be something that's familiar, 200 width or 200 height by 200 width by 3 channels. This 340 comes from the fact that there are, let's see, what was the last one we went through? Test. Yeah, so data, test, and there should be, let's see, yeah. Oh, it's I was hoping it would be ordered in some way that made sense, but there should be around 180 or so images in there that allows us to get from men to women to the, or sorry, the number of files in the man folder and the woman folder to the number of observations that we have here in test. Okay, does that make sense so far? We've been moving kind of fast. Let's hoping we can get to the last part, which will be the most important part. So let's go ahead and look at our data really quickly, just see if things make sense. This little part here, which should be in everyone's notebook, prints out number of observations, and I said like the size. And this is the size of the Y vector, which is the what we'll be predicting. You're going to see here that since it went through all the women folders first, it had the index of 0, and that's how we got the response variable. Okay, so this is another part that I kind of have to do some hand waving through. We're going to be using So there's a lot of different ways that you can extract features from images. One way that would be very simple is to get, what's the maximum, average, and median pixel density within an image. Maybe you want to do that for all 3 channels. Maybe you only want to work in grayscale. And you can also chop up that image into, a n by m grid and look at the pixels within each grid and get information from that as well. So one thing to note is that if we were working with a neural network, you would just feed in the image itself, and the neural network would take care of the extracting features for you. But we're going to go a little old school here and extract the features ourselves. And so what I'm using here is something called Hog Transformation, which comes from this SK image library. By the way, some of these libraries you'll probably have to install yourself. There is a YAML file to be able to do that. And I think there are instructions in the README as well. So really quickly, the Hog Transformation, let's see, where I define it. I think say something about histogram, right? Yeah. So it's a histogram of oriented gradients. And what it's doing is it's taking a grid of the image and then looking at the gradients of or the gradients within that image and where they're pointing to. So if you're something similar would be kind of edge detection, and that might be looking at where the edges are within each subsection of the image. But what's nice about this is you also get the information about the gradient and where it's pointing to. Again, a lot of hand waving there, but maybe I'm hoping it helps kind of see what those images look like. So what we're going to do here is call this Hog Transform on it, which is just a wrapper for this function. And we're going to pass in the small pool matrix. So we're not passing in the image, we're actually passing in the Numpy array. And then what this code does here is it just plots the original image and then the new image. Oh, yep, so I have to instantiate that. And then this might be a little hard to see. Let's see if we can zoom in a little bit. So what's going on here is this is the original image. And then this is the hog features. And what you can kind of see is it kind of makes out the different kind of edges, but also the gradients within that image. And I think up here kind of represents some of the grids that this picture is being chopped up into to be able to extract the histogram of gradients within each grid. Now, I chose the Hog Transformation because it was one that I found, but if you were really doing this for, for real, you want to try a bunch of different transformations to extract a bunch of different features for your data. So let's go ahead and look at some of the features that we got. So this image, which was 200 by 200 by 3, we actually ended up getting a 6,084 dimensional array. And so that now that's something we can actually work with and pass that into some traditional machine learning models. So let's try that again on some of the actual data that we have. So again, what we see is this is the original image, and then this is what the Hog Transformation picked out, which is kind of nice. I mean, it makes sense to us. It's like a nice sanity check that something's going right. Okay, so let me see. So then the next thing we want to do is to, let's see, catch up to where I am here. So what we're going to do here is we're going to iterate through all the data in our data dictionary, which if you remember, it's taking the train, validation, and test set, and then giving us a list of, or essentially a new matrix. And then what this is going to do is it's going to go and get the X data. And then for every image index in that X data, because remember that the X data is 4-dimensional. Actually, why don't I just show you? That's too much otherwise. Okay, this is a really hacky way to stop your code, by the way. Don't do that. So it's 1600 by 200 by 200 by 3. And what this is doing right here is I'm going to iterate through every single row in this matrix, all 1,600 observations in our data. I'm going to go ahead and extract the current matrix for the observation that we're looking at, throw that into the Hog transformation, and then it's going to return back a little extra piece of information that we don't need actually. So that's why I just put the underscore there, and then the actual features that we want. So this is going to take a little while to run, which gives me time to, well, first to stop and see if there's any questions. I know this has been quite the whirlwind. But yeah, does anyone have any questions? Otherwise, I can talk a little bit about fairness here. Okay.
I guess, wait, when did it, I was confused about when did it become 1,600 observations? Because I thought there were like 340 images.
Right, right. So hold on a second, maybe we can look at it a better way really quickly. So the training data actually has a lot of information in it. Well, here, let's open this. So this was the validation data, and that one had around 300, or the testing data, that one had 340. But if you go look at the training data, this
right.
Yeah,
Oh,
that one has a lot more in it. It's actually slowing down my computer to look at it. But yeah, so that's where that 1,600 comes from. And I think, yeah, sorry, up here as well. So we can see that we have 1,600 pictures there, 340 there, 340 there.
And then for your purposes, do those data sets overlap at all? Like, are the validation ones from?
Yeah, so good practice is to make sure that your data sets don't overlap at all. That like, and even better to make sure. So first you want to make sure that you don't have the same observation in your train as your test. That's like bare minimum.
Right.
And then what you want to do is, let's say, I think this data set has some celebrities in it. So let's say that we don't have celebrity A that's in the training data set, also in the testing data set, because that would also bias your performance a little bit. You would, sorry, bias is a little bit of an overloaded term. That would also kind of inflate your performance a little bit. Does that make sense?
Yeah, yeah. I guess, yeah, because I've done some stuff where there's a training set and a testing set. I wasn't really sure whether it's also a validation set.
Right, okay. So there are lots of different ways to kind of tune your model. So if you have a model and you want to tune some hyperparameters, what you're going to do is either have a validation set to tune those hyperparameters on, or you're going to use k-fold cross-validation. And so what that lets you do is give you an idea of what your testing error might look like without actually testing on your test set. Because if you're going to start tuning hyperparameters, you're essentially starting to train the model a little bit by hand. And if you do that on your test set, then your testing error will be artificially lowered, essentially. So what I use here is a train validation test split. You could also just combine the train and the validation together, and then use something like k-fold cross-validation if you wanted to.
Gotcha.
Okay, so it looks like our data is done running. It took a little while because this Hog transformation can be a little bit computationally intensive, but what it did was took those images and converted them into features. So we see that it's still 6,000 by 84. We have this feature list, which looks like this. And let's look at the keys really quickly. So train, valid, and test. Let's look at test. And this is, sorry, this is just probably a little bit much, but what this is the entire validation test set. If you go to the 0th index. Oh, sorry, no. I'm not expecting. Okay, yeah, sorry. So this is a list of our features essentially. And there's 340 of them for the test set. Okay, so a little bit more hand waving. I'm just going to use Nsgd Classifier. I don't understand a whole lot about this other than it's I think some kind of an SVM, but it's just really easy to work with Hog variables or features in this one. So we're going to take this, which comes from sklearn. It's a linear model. And then instantiate. So this basically just tells the this library, hey, we want a new model that has a random state of 23. In order to train this model, you can iterate 1,000 times, up to 1,000 times, or until you converge. And then this tolerance, I think, has to do with SVMs. So we create that model, we call fit on it. And whenever you call fit, you need to provide an X and then a Y. So remember that this data dictionary contains the raw matrix variables for the training, but then also the variables for the Y value at the first index. So you go ahead and train that. And that was really easy. So training models in sklearn is actually really nice. It's literally just you call model.fit X and Y. If you're going to do any hyperparameter tuning, you would do that up here and instantiate different models for every different hyperparameter that you want to do. So let's see how we did. So we're going to use this function, precision recall and F-score support. So that comes from the sklearn.metrics. And all it does is it takes in, really quickly what I just did there, since some people may be new. When you're working in Jupyter Notebooks and you have a function that's either you wrote or comes from a library, you go inside the parenthesis here and hit Shift Tab, and it'll bring up the document string for you and tell you a little bit about what this model or what this function takes in. So you provide the Y true, which is the actual values that go along with the data. That's the ground truth. And then you provide the Y predictions, which comes from a model.predict call. And then you can change a little bit here, depending on your use cases. We don't have to worry about that too much. But what it's going to return is, let's see, precision recall F beta score, which is a F1 score if you don't provide any other information, and then support if you want it to. So we're going to call, we're going to take our class or our model that we just trained. We're going to call predict function on it, and we're going to pass in the same exact data that we passed in the first time to train it, just to get an idea for like how well is it performing. So I think it was recall, I've already forgotten. Oh no, precision recall in F1. So this is really good. Well, on the training data anyway. So what happens a lot is you train a model on the training data, it may overfit, which means that what it's doing is it's really learning what's in the training data, but it's maybe not able to generalize to new data. So that's why you want to keep your training and test and validation split separate if you can. So to make things a little bit easier, there's a wrapper function just called assess performance, where you pass in the model that you want to use, hopefully it's already trained, the X data that you want to evaluate on, and the Y data that you want to evaluate on. And this positive label is, I'll explain that in a bit, but the positive label is either 0 or 1. So we can go ahead and instantiate that. And then let's look at how we did on the train again and valid. So really good on the train, like we already know. And then the validation set dips a pretty good amount. I mean, this isn't terrible, but it probably means that we're a little bit overtrained. But you're probably never going to get this validation performance up to where the training performance is, unless you're just really good at what you're doing or something went terribly wrong. It's sometimes hard to tell the difference. Speaking from personal experience. Okay, so now we're going to assess fairness. And this whole code chunk is not something you have to write. But what it is here is I downloaded a new data set that we can parse on. And so, or so that we can evaluate our model on. So this would be an even better test set than the one we have above. But the reason I'm using this is because this data set has not only gender classification for every image, but also race and ethnicity classification for every image. And again, they did it very simply. They did 0, 1 for male, female, and then I think they had 4 classes for race and ethnicity, which was, I think, white, black, Asian, and the other one might have just been other. I think that's usually what people default to, which I always draw a little bit of ire at, but because usually I fall into the other category. But if you go and look at this UTK faces data. So hopefully it opens. It doesn't crash or anything. Let me try and open it up in my file browser really quick. Let's see. Seems like data saves. Okay. Yeah, it crashed a little bit, but I think everything else should still run. Basically what that is just a bunch of data with the actual name of the file has the information on age, gender, and race. And so what this does is it takes that file name and then parses it a little bit to see, I only look at people who are below 80 and above 20 and whose race is either white or black, because that's what our data looked at. So we can run this data with code. And this one actually does take a little while to run, unfortunately. But now I can talk about the fairness that we'll be working with. So the fairness code that we want to be writing for this, let me bring it up really quickly, is something called a performance gap. So all we're going to do is we're going to look at performance between overall, which we've already done, and then we're only going to look at women, men, black, white, and then to do a little bit of what the gender shades paper did, we're going to look at black women and then white women. Oh, cool, that one opened from here. So this is just a giant data set, which I'm going to exit out of before I freak my computer out too much. So it's important to note that the gender shades paper, what they did was they didn't exactly use race. What they used was, I think they used a Fitzpatrick skin tone scale, which they were able to parse people out into dark skin versus light skin. And the reason for this is because using race and ethnicity as a stand-in for how dark your skin is just not a very good system. There's a lot of within group variation. And so that is one drawback of the work that we're doing here. But it will serve as an example to look at fairness. So we have a little bit of time while this is running to do this. So what we're going to do is we're going to take some of the code that we wrote up here and paste it down here. What we're going to be using is the data that comes out of this. So this x underscore UTK and y underscore UTK, these are all the Hog transformed features, and then these are the labels. So what we can do is we can go in and replace this x with the new data, and then the y with the new data as well. So the thing is, we're not retraining our model. We're using the same exact model that we trained before, but now we're going to look at, how does this model perform on a completely new data set, which is what the gender shades paper did. So this will give us an idea of what the overall performance is, but we also want to be able to look at only women or only men as well. So we're going to use a couple of variables for that. So this y underscore UTK is going to be binary, zeros and ones, 0 meaning that the class is woman, 1 meaning that the class is man. We also have this race underscore UTK, which will tell us whether the individual for that image is white or black too. So we're going to create what's called a Boolean mask. And all this is let's go women equals y underscore UTK equals 0. And I'll show you what this is after this is done running up here. But all this is just, it's going to be the same length as y underscore UTK, but now we can use it to index into the data that we want, because this is called something called Boolean indexing. So we go here, and then we provide this where the rows are, and then we say, and then everything else is all gravy. And then we do the same thing here, but because this is a slightly different shape, we only need to do this, but we don't need to include that part. And this is where the pause label comes into play, because F1 precision and recall will mess up a little bit if you don't provide a Y matrix or a Y ground truth that has all the classes in it. It has to have at least one positive, one negative class. But because we're only looking at women, it's only going to have the 0th class. So we're going to say that the positive label is 0, and that'll allow it to run. Otherwise, it wouldn't know what's a positive label, and that will kind of cause it to error out. This is almost done, and we're coming up on time, and I want to get through this and then kind of leave some questions at the end for people to kind of work through. Okay, so let's make sure it ran. Okay, so this is a code that I copied and pasted from before. I should probably turn this into a function so I'm copying and pasting it everywhere, but that's okay for now. This is the new data, the UTK faces and Hog transformations. Things seem to work pretty okay. So let's go and see how we perform on it. The performance is even worse than our validation set, which again makes sense. This is a true test set that's drawn from a completely different distribution, different data. So it makes sense that the performance has gone down. So this is the overall performance on everyone in that data set. One important thing to look at here is how imbalanced this data set is. So like our data set, it has a pretty even balance between men and women, but it's pretty terribly imbalanced between white people and black people. Which if you're not careful, more than likely if you're just going to scrape websites for data or just raw data somewhere, you're going to see an imbalance like that. So it's always important to look at that. So we look at this for women, we actually see that the performance goes up. That's not something that they saw in the gender shades paper. What they actually saw was that the performance went down for women. And I'll talk a little bit about like what you should do if you see something that like doesn't make sense, or even just ways to analyze differences in fairness. So let's look at this for men. Go ahead and do this, and then we take this mask and put it, copy and paste it here. We do need to remove this because men have a label of 1, so the positive label is no longer 0. So better than overall, but worse than women. And then we also do this starting for race as well. So the way we're going to do this, and then I'm just going to start copying and pasting code pretty soon after we kind of get an idea of what's going on here. But we take this race underscore UTK, which is going to be binary, which is the 0s and 1s. Can I call meeting like that? Oh, I can. So that means there are some 1s in there for that are representing black people in our data set. And that's what we're going to use to index to look at either only black people or only white people. So we're going to take this, and I think 1 is black, and then we're just going to do mask black. And then put that here, put that here. Okay, so what we're seeing here is that overall for black people, this model does slightly worse, but not significantly. Again, what they saw in the gender shades paper was that the model did significantly worse. And part of the reason for this might be because we have such a small pool of images of black people in this data set. So I'm going to start copying and pasting some code really quickly. This code is available to you on the GitHub if you need it. Just so we can get to the end of this really quickly here. So let's see. I'm pasting here. So this is a mask for only white people in the data set. We see that this is a little bit better than the F1 score here. Precision and recall are kind of variable actually. And if we only look at black women, what we're going to do here is a Numpy logical combination. So what this does is it takes a Boolean array of mask women and then mask black, and then does a logical AND on them. So false and false becomes false, true and false becomes false, because what we want here is only people who are black women essentially to look at performance. So the 106 black women's data set, and we see that the performance is really good. Again, not what we expect, but that could be a fluke because only 106 people in the data set are black women. So then we can do the same for white women. And then let's quickly do this for black men and white men too. We have to change this. Yep. So here's where we start to see a significant dip. The F1 score is a lot lower. Precision is pretty high, but this is brought down. But the F1 score is brought down by the recall. And this versus white men. This is a much larger gap, more than you would expect. So overall, we were able to kind of replicate some of the results that was done by the gender shades paper. But some of the issues are that in their paper, they looked at skin tone instead of just race, which is a much better classification for these purposes. They also balance their data set at the very end to assess fairness, which ours is pretty imbalanced. And so my guess is that if you were to bootstrap this, that is run this a bunch of times with bootstrap data drawn from images of Black men, you'd see a lot of variability here and probably for the women as well. And so that's kind of the next part of this, is that like, okay, we're seeing a difference. Is this difference statistically significant? So you want to do some significance tests there. So one thing we didn't do very well is explore the data set, just the image that we have, to see if there's any differences between them. So this would be our pictures of Black men or white men. Is there differences in lighting, in location, the centering of the shot? Are they smiling or not? Differences like that. And so we could also see, if someone were actually to try this, they might tune their hyperparameters, and that might change the results as well. But overall, this is just kind of an indicator of our model does have some bias in it, and that's where the real work starts of trying to fix that bias. So that's all for my presentation. Thanks everyone for showing up. I know that was quite a bit of a whirlwind, but I'm happy to discuss anything after the fact.
Oh, that's really cool. Thanks, Oliver. I actually have one real quick because I do have to go to another meeting. I'm wondering when is the day we're going to stop heavily relying on these cross categorization of people.
Yeah, it's hard because especially in health informatics or clinical informatics, it's really important to be able to like use some kind of categorization like this to look at health disparities. But at the same time, they are pretty they're not that great. And so my hope is in the future, we can look at race and ethnicity, but maybe we can define them in ways that make more sense for the context of their use.
Yeah, I'm wondering
what that means is kind of difficult.
Yeah, I'm wondering if we can they still have that served as like a response, or known as one way to like validate models. So in the models, you don't actually input that in there. You just use variation and data that's collected, and then use that to train your models, and then use categorization of people and see, does my probabilities for predicting things change systematically based on these other things? I mean, I would think that might be good to do, but
yeah, that's absolutely something worth exploring, I think.
Yeah, there's a whole other thing about latent factors and that's why like in GWAS we use the top 10 principal components, because they have enough variation in like special data sets or something. Anyway, great talk. Love that. I'm gonna check out the repo.
Yeah, and the resources I have in here too are they've been really informative for me in my research on this kind of stuff too.
All right, cool. With that, Jordan, you got that.
Yeah, I mean, I think we covered it. Great talk, Oliver. I really enjoyed the context, highlighting some of the caveats and improvements that can be looked into, and the coding was very clear and interesting as well. Thanks again.
Yeah, thank you.
All right.
Cool.
Yeah,
All right, everyone, guys. See ya.